Lecture 14, Early Termination, Reduced Resource Computation. Here's the thing, knowing when to quit is wise. In a program context, we can sometimes speed up our program by not waiting for the slowest steps to be done. This is somewhat related to speculation, in that the topic we've just come off of is about, well, we're doing extra work just in case, whereas with early phase termination, we actually skip some work even though we're supposed to do it on the basis of close enough is good enough. All right, we'll see that's not always a slam dunk, and there are times where that's not okay, and we really do need to be super precise. But there are some ideas where we can investigate when it makes sense to apply it. But there are two basic ideas that we're going to talk about, and one of them is skipping some work, so just don't do it. Just don't do it. We don't need it, or we do need it, but it's not that important, so we'll skip it. And the other idea is to deliberately reduce accuracy to speed things up. And you might implement both of those strategies when you're writing an exam. It's more of a concern for the writing an exam by hand in the pack with 2.5 hours time limit kind of thing. But you could implement both of those strategies. Time is limited, and you might choose not to do a question because the benefit is small, and you would use your time more efficiently by doing a different one. So you choose, I'm going to just leave question 3.2 blank, and I'm going to work on question 4.1 instead. Perhaps because question 3.2 is not worth very many marks, and question 4.1 is worth a lot more. So in that case, you take the decision, it is actually more efficient for me to just skip this, and we don't have time to do everything, we'll do question 4.1. Alternatively, another way that you could do this is you could skip error handling in question 4.1. You'll lose some marks in that question, but it takes less time and frees up some time where you could do question 3.2 instead. So in the first case, you skip some work totally to basically get it over with faster. Should you answer all questions on the exam? Yeah, yes, but do you have to? No. The grade that you get will reflect that you didn't do that question, but that's sometimes acceptable. The other approach is you are reducing the accuracy of a particular question so that it's done faster. We complete 4.1 in less time, and that allows us with more time to do question 3.2, knowing that we're trading off some marks here for some other marks there. Exams are nice, or maybe nasty, in that you could do either of those things. Your program might support only one of those. Whether or not it makes sense to do a particular strategy in your course in your program depends, of course, on what the nature of the work you are doing is. So we're going to start with early phase termination. This is a formal name for the idea of quitting early. So we've talked about barriers. And a barrier in the context of synchronization is we wait for all of the threads to gather up, and the idea is that no thread may proceed past a barrier until all of the threads have reached that barrier. And this might slow your program down because maybe one of the threads is very horribly slow and gets there a lot later than all the other threads. Well, one solution is kill the slowest thread. We were expecting 8 threads to get here, and one of them is taking too long, and oh no, it had an accident, and will no longer be arriving. And then in that case, everybody's here, and we can proceed. Well, that was easy, wasn't it? Oh no, that's going to change the meaning of your program. In some strict sense, yes. The question is that acceptable as a distortion? Does it matter? Is it okay? Will we get a reasonable result in spite of this? We don't want to be completely crazy. The killing is my business and business is good approach is not ideal. we can develop a statistical model of the program behavior, and that will give us some idea of when it is okay and what tasks we can kill so that we don't introduce unacceptable distortions. And then when we run the output of the program, it is what we normally would expect with some confidence interval. That is, with a little bit of uncertainty. If that doesn't matter, it doesn't have to be super precise, we're fine. Here's an example of early phase termination. Pretend you're really bad at Mario Kart. If you're in last place when the second last player or the second last AI crosses the finish line, the race is over at that point. We already know you finished last. As Mario would say, oh no. There's no benefit to making everybody else wait while you have to drive the rest of the lap to the finish. In this case, ending the race while one driver has not yet completed all laps and made it to the finish line is safe because the outcome is already known. I'm really bad at Mario Kart. It doesn't change the outcome. There's no unacceptable distortion that's created as this. If you let the person actually drive all the way to the finish, you would have a more precise value for the time it took them to complete the course. But maybe no one cares. You're in last place anyway, and the outcome of the race is based on how everybody finished, and the time splits are not important. Here's another idea for doing early phase termination. And some kinds of problems are mathematically hard in nature. We call them, in a formal sense, NP hard or NP complete. And basically, the long and the short version is if you want to find the absolutely most optimal solution, you have to consider every possibility. And what my strategy presupposes is don't. We don't have to have the perfect solution. Having a good solution is sufficient. So, if you are Bugs Bunny and you are trying to get somewhere and you should have made that left turn at Albuquerque, you could think about, what we sometimes refer to as the traveling salesperson problem, for the sake of an example. There are endpoints on the map to visit, and you want to minimize the amount of travel time. And although it's very easy to compare solutions, you could compare them based on kilometers traveled, for example. It's hard to be certain that the one that you are looking at is the absolute best route, because you have to consider every possible one to be sure that it is. Okay. How would we improve on this? I mean, at the one end, you could just pick a solution. You could say, all right, whatever solution we come up with first, that's the one we're going to do. That will probably not be optimal. There might be a lot of backtracking on this, and it might be kind of inefficient, and there might be a significant cost to doing that. Making somebody drive 800 kilometers for a journey that could be completed in 400 is not ideal. We're wasting time, we're wasting fuel, we're wasting money, so that's not good. On the other hand, trying every possibility, if we have a small number of places to visit, if there's only 5 places that we're going to visit, sure, you can try every possibility, because it is a tractable number. But for a more complicated problem, we maybe need something better than this. So one way that we could know that we are wasting time is to remember previous outcomes. So as we are composing the route, we say drive here from point 1 to point 2 to point 3. We can keep account of the travel cost in units. I'll say it's kilometers in this situation just for the sake of having something easily comparable. Time is a little bit harder to use as your units here because, as you know from rush hour and traffic jams and what have you, it can vary a lot by time of day. But if our currently accumulated cost in kilometers is larger than the solution that we have got in hand already as our previous best solution, then, don't keep calculating the rest of this route. If we've added points 1, 2, 3, 4, and 5, and this is already worse than a solution that we already know, there's no point in figuring out what to do with 6, 7, and 8, because it's worse. If we have a route that's 400 kilometers already, and we are partway through building a solution and it's 412, just don't evaluate the rest of it, and any descendants of that route. Right? When you are evaluating a route, if there are 3 more stops, we have to consider, okay, given that we've done steps 1 through 5 here, what are all permutations for 6, 7, and 8? Don't have to do any of them. Can skip them all, because we know that it won't be any better than what we've already calculated. So, do you have another idea? Well, another idea is that you can stop as soon as you have a solution that is reasonable. If we are given a particular target, and say the goal is to get total travel under 500 kilometers, obviously your target has to be reasonable. It can't be, you always have to be perfect, otherwise we don't save any time. But if the goal is to make total travel under 500 kilometers, we can stop searching as soon as we find something that meets this constraint. So that might mean that we stop at 499 kilometers and the optimal solution is 400, meaning that there's actually 25% more driving for the person who is actually going to take this route. However, it does not mean that this is a terrible outcome. If it meets our criteria, we've said anything under 500 is acceptable, 499 is under 500, and we'll say, yeah, we'll go with that. If the traffic in the hypothetical region is anything like that of the GTA, the route that's shortest in kilometers is maybe not the shortest in terms of time anyway, and so trying to micro-optimize on the kilometers isn't always going to produce the best outcome. That it may be the case that where you're driving, the shortest route is, for example, driving down Yonge Street, but actually that's really inefficient in Toronto because there's a lot of traffic lights and there's a lot of intersections and there's a lot of traffic and a lot of on-street parking and what have you, and it might actually be more efficient to drive over to the highway and take the highway where you're going, even though it's longer in kilometers. So it's okay if we find a satisfactory route, that's probably fine. We could also reduce the amount of effort by choosing, say, at random 5 or 10 different possibilities, and just evaluate each of those and see which of those is the best. There's no guarantee in that case that you'll get an optimal solution. You might have, just by chance, chosen all of the 10 worst options that could exist, but you will probably get something that is plausible, probably get something reasonable, and it also allows you to compute in a fixed period of time how long we are going to travel. So that fixed period of time has a certain benefit. If this is a user is asking for it on Google Maps, then giving them an answer quickly is helpful. The user wants that. We don't have to spend 5 whole minutes calculating every possible route to produce an optimal solution. Just I'm trying to get from here to the hardware store. Give me directions, please. It will do it. Here's an interesting thing to think about. What does Google Maps do? That's actually kind of like an interesting idea to speculate about, and in an in-person lecture we could actually spend some time hearing from people and hearing what they think, because I don't know that there is a published answer of this is how Google Maps does it. For some problems, there are relatively few solutions. If you are in the Yukon Territory and you are asking for driving directions, the set of roads that you can travel is pretty finite, and you can pretty quickly identify this is how it's going to go. And in such a remote place where there aren't very many roads, it's probably possible to try all possibilities, or at least zero in very quickly on a good option. If, however, you're driving in Toronto, Toronto has a grid system. It's by no means perfect, but it is relatively regular. And that means there's a lot of options. Do you drive, when you're driving from here, do you turn left on this street and then right on that street and, then continue back and turn right somewhere else and turn left? Or you just go straight and turn left later on? There's a lot of possible options because of the grid structure, where you could go, well, if I go down south 2 streets and then, turn right on there, it's a one-way street, which might be faster than moving along one where, people are making left turns. It's complicated. It's complicated. I mean, maybe a heuristic is used to generate possibilities, and the best ones of those are chosen. In a previous final assessment question, I asked people to speculate about some different strategies for how this might work. You could remember what people who are driving from this point to that point have done in the past and how well it worked out for them. That makes sense if you're driving between sort of two well-known points. So if you are departing from a hotel and going to an airport, it is something I'm sure that other people have done before you, in which case, yeah, we can remember, all right, well, people who drove using this route, taking the highway, blah, 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 got there in about this much time, and that is helpful. There's a lot of inputs because there's information about the streets and their speed limits, and you can get data from drivers who are currently on those streets about whether there's traffic, anything like that, which potentially changes your answer, so there's a lot to consider. But ultimately, there's probably some sort of pathfinding algorithm, A star or something to that effect, which is used to ensure that you're making progress getting closer to your target, right? So that if you get to an intersection, it won't consider a route where you turn left and that takes you away from the destination, most likely. Again, but there's probably an exception to that because there are situations where, well, actually the fastest way to get somewhere is to first drive in the wrong direction and then get on the highway, and then using the highway travel some larger distance in a shorter time, hopefully, if it's not the Don Valley Parkway, and then you can get off the highway closer to your destination and have a smaller amount of city traffic, which will hopefully get you there sooner. I don't know. There's a lot to think about, and there's a lot of different possibilities, and I encourage you to invest a little bit of time thinking about how would Google Maps do it? How would they suggest to you the route or route options that you want to take to get from here to there. All right, moving on from that, the next thing that I want to talk about is trading a bit of accuracy for performance. And the idea here is that Monte Carlo simulation is a good candidate for this. And it is, you can do this for ray tracing as well. But the idea is that for mathematical functions that are, in a vague sense, not nice, different points might take longer to evaluate than others. And when it comes down to it, do we need to have a mathematical function calculated to a great deal of precision? Maybe not. I mean, with a ray tracer, you're already picking points randomly, and in either case, you are spawning a lot of threads, and you could wait for all of them to complete, or you can kill ones that are taking too long, if there are hopefully not too many, and then compensate for missing data points. So if you have a graph which appears otherwise to be continuous, and you have a little point missing, you can just fill in and say, yeah, I'm guessing that the point in the middle neatly connects the points on either side. If you are rendering graphics or something like that, if rendering a particular pixel didn't work, you don't have to retry it or you don't have to wait for it. You could just average the surrounding pixels, and most people probably would not notice the difference. Even a 1080p screen, that's 1920 by 1080 pixels. That's a lot of pixels. So if a couple of them are missing here or there, and you just compensate by averaging some nearby pixels, it maybe makes an edge look a little bit strange, but it's unlikely that you're seeing individual pixels unless you're sitting really close to the screen in question. So you may not even notice that there is a slight distortion in this one pixel here or there. On the subject of that, there's also the idea of calling the election. This was written long before November of 2020, let me tell you. But in some cases, results take a long time, but we don't need all of them to produce a result. In a situation where the majority wins in some protocol, if it's database and it's a distributed database and they're electing a leader as the database, if there are 5 nodes and 3 of them have voted in favor of node 2, we don't need the other results. We can stop as soon as sufficient results have been returned. It's either there's an outright majority for a particular option, or the remaining votes are insufficient to change the outcome. As I'm sure you have become acutely aware if you watched any of the U.S. election results in 2020, this happens with election projections. Even if not all polling stations are reporting a result, news channels declare a winner if the remaining votes would not be enough to change the outcome. And actually, sometimes, if the state is not super close, news channels probably declare a winner even if the outstanding votes exceed the margin, on the theory that it won't be the case that they are 100% for the candidate who is in second place. If candidate A has been winning 70% of the vote in this county, they probably won't expect, all of a sudden that 100% of the remaining votes will go to candidate B. They could be wrong. The Dewey defeats Truman picture is kind of a way of reminding yourself that predictions are only predictions, and calling the election can be wrong. And of course, in 1948, the election was called for Dewey by the Chicago Daily Tribune, and that was not correct. Okay. For some categories of problem, we actually know that not only a solution will exist, but also how many steps it takes to solve in an optimal scenario. And consider, for an example, the Rubik's Cube. The Rubik's Cube is much easier to explain if you've ever seen one and held one in your hand before. And if you're just reading the notes and watching this, it's not as tactile, but I'll show you a quick example. Anyway, this is a problem with a very large number of permutations, right? The cube has colors on all sides, and you start by scrambling it up, and then you try to make it look like it looks in the picture, where all colors are on one side only. Now, people have done some research on this, and they've proven that no matter what the initial state of the cube is, it can be transitioned to a solved state in 20 moves or fewer. This number is referred to as God's number because it is the maximum number of moves it would take for an all-knowing deity to solve the puzzle. Now, if you have a solver for a Rubik's Cube and you don't find a solution in fewer than 20 moves, you could actually cancel this solution attempt and try another one, because you know that it's not the optimal solution, right? We know a better one must exist because there always is a 20 move or fewer than 20 move solution to the problem that you are facing. That's fun to talk about, actually, but let's see what happens in action. So we're going to go to this website, Rubik's Cube Solver, and try it out. Okay, so let's see this in action. It runs an open source algorithm, this website, and given a particular Rubik's Cube, we can scramble it, and then we will ask the solver to run. And it will calculate the solution, and we will wait patiently as suggested. Now, I want to point out that this is literally the first one that I wanted to demo today. And sometimes it produces a solution very quickly, and sometimes it produces it very slowly, and this is obviously a slow one. And I honestly did not edit this in such a way that the first one we looked at was somehow not optimal. That's just the luck of the draw. In any case, as you saw, we produced a solution with 21 rotations, which is to say this is not the optimal way to solve the puzzle. However, it was taking too long for the solution to be calculated with 20 moves. And in this case, it gives us an answer with 21 rotations. Based on my observation of this website, I think if it gets to 80% on the progress bar without finding a solution in 20 moves or fewer, then it relaxes that constraint and says, all right, I'm willing to accept a solution that is more than 20 moves. And of course, it gives you all the steps for how actually to solve it, and that is the solution. And it is 21 moves, and you can even, if you're so inclined, watch it show you how everything looks, and it changes the little tiles so you can check and see that actually what you're doing matches what is supposed to happen. Okay, let's try again and see what happens in perhaps a different outcome. Maybe we'll find a better solution a little bit faster. Yeah, here we go. This one found a solution under 20 moves, and therefore it is found quicker, because as we were evaluating solutions, we came across this one much sooner, and it is much quicker to actually execute. There's not as many things. And yep. Let's try one more. See how our luck holds up. All right, and here's one that is solved in exactly 20 rotations, and that is reasonably as expected. Honestly, I did not edit this video so that the 3 possibilities that we tried were all in a row. I just went to the website. It was recorded in one take, and it just so happens that the first one was more than 20, the second was fewer than 20, and then the third one was exactly 20 moves. You can't plan for this, and that's quite a lot of luck on my part, I suppose. So I guess I'm not going to any casino anytime soon. Not that I'm really into gambling. In any case, if we are looking at this and we are thinking about what kind of trade-offs happen in this solver, we actually see 2 kinds of trade-off. One is that if we are taking too many steps, then it won't be considered a viable solution, and the open source algorithm says don't do it, we're just going to skip it and go on to evaluating the next possible solution. The other thing that we see is that if we don't get an under 20 or equal to 20 move solution within a certain time limit, it returns a solution that takes more than 20 steps to give you a less optimal solution in a faster amount of time. The most I've ever seen out of this is 24 steps. I'm not sure if it would return you a solution that's anything more than that. That's the maximum that I have personally seen in playing around with this, but I can't say for sure that it is the maximum that it would ever return. In any case, that second idea of reducing the accuracy, that is the quality of the solution for speed, actually leads us into our next approach, in which we are going to talk about reduced resource computation.